Okay, let's dive right into this explainer and explore the incredible, completely invisible mathematical balancing act that keeps our power grid running smoothly and affordably. Every single time you flip a light switch or plug in your phone, a massive, continent-spanning machine instantly responds. But managing that response, well, it isn't just about throwing a giant lever somewhere. It's actually one of the most complex mathematical optimization problems in human history. And when this math fails, even for just a few minutes, the consequences are disastrous. We're talking anything from astronomical surges in your energy bills to catastrophic region-wide blackouts.
Just imagine the sheer scale of this task for a second. Grid operators have to perfectly match electricity supply with your exact daily demand, second by second, all while obeying some incredibly strict physical laws. You see, the grid has almost zero storage capacity compared to what it actually uses. If operators generate too much power, the grid's frequency spikes, which can literally fry massive electrical transformers and severely damage our infrastructure. But if they generate too little, the frequency drops and we get immediate rolling blackouts. And they have to execute this flawless high-wire act while balancing a massive portfolio of wildly different power plants.
So, have you ever wondered exactly how the grid decides which power plants to turn on to ensure your lights work at the absolute lowest cost possible? It is definitely not as simple as just turning on the cheapest plant and leaving it running all day. System operators have to constantly forecast demand and adjust the supply, minimizing production costs while maintaining unwavering stability. Solving this daily puzzle relies heavily on two completely distinct, massive mathematical processes that dictate the fate of the grid every single day: unit commitment and economic dispatch.
Here's our roadmap for today. First, the power grid puzzle. Second, understanding unit commitment. Third, economic dispatch and power flow. Fourth, commitment versus dispatch. And fifth, how the math is solved.
Section 1. The Power Grid Puzzle. The delicate balance of keeping the lights on.
To really get this, we first need to look at the money. Producing a single megawatt is dictated by a highly complex financial function. Operators have to consider variable costs, which basically change based on how much power is actually being made. This includes the price of the fuel being burned and the generation efficiency. That's the rate at which the potential energy in that fuel actually converts into electrical energy. But on top of that, power plants incur massive fixed costs. The initial plant construction, property taxes, base operations and maintenance. These are hefty bills that exist whether the plant is running at full blast or just sitting totally idle.
Now, in a perfectly competitive market, grid pricing revolves around this concept called short-run marginal cost, or SRMC. That is simply the cost of producing just the very next megawatt of power. Think of a power plant like a massive bakery. The SRMC is really just the cost of the flour and yeast for the very next loaf of bread. But the bakery still has to pay its massive monthly rent, right? Because operators have to cover those massive fixed facility costs, power markets rarely operate on pure SRMC pricing alone. This financial reality forms the complex baseline for how the grid software decides who actually gets to sell power.
Section 2. Understanding unit commitment. Choosing the active roster.
So let's talk about unit commitment. Think of it kind of like a sports coach deciding exactly which players are on the active roster for the big game, based on their availability, stamina, and of course, their contract cost. Before you can decide how hard a power plant should run, you first have to make the binary decision of whether it should be turned on at all. The grid operator essentially plays the role of that coach. But here's the kicker. They have to make these roster decisions a full day in advance. Why? Because some of their biggest players, like massive coal or nuclear plants, take 12 to 24 hours just to warm up their boilers and sync to the grid. You see, a power plant isn't just a simple light switch you can flick on and off. It has intense physical ramping and resting requirements that create an absolute mathematical headache for the software. For example, a large thermal plant might have a minimum stable operating level, meaning once it's on, you can't just run it at 1% capacity. It has to run at 40% minimum, or the flame literally goes out. Furthermore, if you commit a nuclear plant to the grid, it might have a mandatory minimum uptime, requiring it to stay on for several days. These physical limits create a massive class of optimization problems just to figure out who's even playing in the game.
Section 3. Economic dispatch and power flow. Navigating the physical limits.
If unit commitment was the coach picking the active players before the game, economic dispatch is the act of calling the minute-by-minute plays while the game is actually happening. But there is a massive catch here. Before we dispatch the power, we must remember a harsh reality. Electricity doesn't travel however we want. It travels strictly according to Kirchhoff's circuit laws, always following the path of least resistance. You can't just tell an electron to take highway A instead of highway B to avoid a traffic jam.
So the simulator wants to calculate the exact flows in the alternating current network that result from our chosen generator dispatch.
To maintain absolute electrical stability, the grid's optimal power flow software calculates these exact network flows to ensure they stay within strict physical limits. Transmission lines have thermal limits, which are basically just megawatt limits on the flow, so the metal wires don't literally overheat and melt down. But critically, the dispatch must also survive contingencies. Say a tree falls on a major transmission line and shorts it out. Well, the software must have already positioned the power dispatch so that the surrounding lines can instantly absorb that redirected surge of electricity without melting down themselves.
Section 4. Commitment versus dispatch. The binary versus the variable.
Let's deeply contrast these two fundamental concepts so we can really understand why getting them right keeps our power affordable. On the left side, unit commitment is a purely binary integer decision. It's the 1 or 0, the on or off. It looks far ahead to ensure enough of those sluggish plants are awake and ready to go. On the right side, economic dispatch is a continuous variable decision. It takes those units that are already on and precisely dials their specific output, say 55.4 megawatts, adjusting constantly in real time. And splitting these into two steps is strictly necessary. Trying to solve the binary on-off combinatorial math at the exact same time as the real-time continuous AC power flow equations would simply take too long for any modern computer to solve before the lights went out.
Section 5. How the math is solved. The software behind the grid.
To crunch these millions of variables without crashing, transmission organizations use advanced mathematical programming and highly specialized software suites like GE Maps, ProMod, or ETAP. For instance, they rely heavily on a technique called mixed integer programming. This is specifically required because of that binary on or off nature of unit commitment we were just talking about. The math has to handle integers for the on-off status, mixed right in with continuous variables for the exact megawatt output. This incredibly dense math runs quietly in the background of wholesale markets, simulating production and analyzing short circuits to ensure the grid is both economically and physically robust.
But because power markets rarely show pure, perfect competition based strictly on those short-run marginal costs we mentioned earlier, simulators must also account for human behavior. Generators might try to bid strategically, essentially gaming the system to maximize their own profits rather than just offering their true base costs. To handle this, the software uses game theory models like Cournot or Bertram competition. By simulating these different types of imperfect competition, the software tries to predict how power plants will actually bid on the open market, providing grid operators with highly realistic, battle-tested forecasts of future power prices.
When you finally marry that binary on-off roster decision with the minute-by-minute economic dispatch, and then wrap the whole thing in a safety net of contingency planning, you achieve the absolute holy grail of grid operations: security-constrained unit commitment, or SEUC for short. This process requires a staggering amount of sheer computing power, solving literally millions of equations simultaneously. It is the ultimate mathematical safeguard. It guarantees that the schedule of generators we commit to using will not only be the absolute lowest cost to consumers, but will definitively keep the lights on, even if a major power plant suddenly trips offline.
All of this really leaves you wondering. This math was originally built for the predictable, slow-moving world of giant coal and gas plants. But as we transition to a modern grid filled with a lot more chaos, where a passing cloud can instantly shut off a massive solar farm or a sudden gust of wind spikes production, the math behind unit commitment and economic dispatch is only getting harder. As our energy sources become completely dependent on the unpredictable weather, are our algorithms and computers going to be fast enough to solve this puzzle and keep the lights on?